we had left in the classroom, our topic is related with matrices titled as the inverse of a matrix. We are already well aware of the multiplicative inverse of real numbers. In real numbers, the multiplicative inverse for a number x denoted by 1 over x or x power minus 1. This is our number which when multiplied by x yields the multiplicative identity. Similarly, multiplicative inverse of a fraction, let's say a by b, is b by a. In other words, when we multiply a number by its multiplicative inverse, we get what? In matrices, the multiplicative inverse of a matrix is a matrix that gives you the identity matrix when multiplied to the original matrix. In this definition, A is an n cross n matrix and another matrix C having the same order is called the multiplicative inverse of the given matrix A if AC and CA both are equal to I, where I is the identity matrix of the same order. Next definition is about the invertible matrix. If the inverse of a square matrix exists, it's called an invertible matrix. In this case, we say that A is invertible and we call C as inverse of A, as described in the above definition. It's always true that the inverse of a matrix is unique. For example, if we consider that B and C are the two inverses of a matrix A, then we observe that B, which is equal to B into I, because the product of any matrix with identity matrix results the same matrix, and I can be replaced by AC because we know that C is the inverse of A and the product will definitely be equal to identity. It can be written as BAC. Again, BA is equal to I because B is the inverse of A, which we have supposed, and the product of identity with C matrix results the C. We conclude that P and C are equal. Thus, when A is invertible, its inverse is always unique. The inverse of A is oftenly denoted by A inverse as shown. So that the product of A with A inverse and the product of A inverse with A results in identity matrix. A matrix is not invertible, sometimes called singular matrix. A matrix which has no inverse called singular matrix, and the non-singular matrix is a matrix which is invertible, whose inverse exists. And it is not necessary that a matrix always has its inverse. A inverse is in fact the n cross n matrix corresponding to the n cross n matrix A. It satisfies the discussed property that A inverse A is equal to A inverse, and both are equal to identity. Let's see an example. Here we discuss two matrices A and C with different entries. We get the product of A and C. We observe that the product of these two matrices is an identity matrix. And similarly, pre-multiplying C by A, we obtain the same result, that we obtain CA is equal to identity matrix of order 2. Thus, C is the inverse of A. We conclude here that C is the inverse of A. This is the statement of a theorem. Let's take a matrix A with entries A, B, C, and D. If AD minus BC is not equal to 0, then A is invertible or non-singular. And the inverse of A is equal to 1 over AD minus BC with the adjoint of A, which is obtained by interchanging the places of the entries of the main diagonal and the sign of the remaining entry. If AD minus BC is equal to 0, then A is not invertible, or it's called singular matrix. This quantity AD minus BC is called the determinant of A, and we write it as determinant of A is equal to AD minus BC. And this implies that the matrix A is invertible if and only if the determinant of A is not solved. Another example, we have to find the inverse of matrix A. We have determinant of A, which is the obtained by multiplying 3 by 6 and 4 by 5. The difference is minus 2, which is not equal to 0. Therefore, we can conclude that A is invertible. If A is invertible, we find its inverse by taking the adjoint of A, which has the entries 6, minus 4, minus 5, and 3. We divide this adjoint by the determinant of A, which is minus 2. And simple manipulation yields the inverse of A, which is shown at the end. This is the theorem which has 3 parts. The statement says that if A is invertible matrix, then the inverse of A is invertible. If A is invertible, then its inverse is also invertible. And the inverse of inverse A is equal to A. In B part, there are 2 matrices are given if A and B are n cross n invertible matrix. A and B both are invertible. Then so is AB, and the inverse of AB is the product of the inverse of A and B in the reverse order. That's AB whole inverse is equal to B inverse A inverse. In third part, if A is invertible matrix, then so is A transpose. If A is invertible, then A transpose is also invertible. And the inverse of the transpose of A is the transpose of A inverse. That's A transpose inverse is equal to the transpose of A inverse. This is the proof of part A. We must find a matrix C such that A inverse C is equal to identity and C A inverse is equal to identity. However, we already know that these equations are satisfied with A in place of C, and A inverse is the invertible and A is the inverse. In this part, we see that A inverse C is equal to identity matrix, mean 2 matrices having the product identity or the multiplicative inverse of each other. And in second part, let us take the product of AB with B inverse A inverse, what will result it? We combine B and B inverse in the middle, which is equal to identity because B and inverse of each other are multiplied. So therefore A identity A inverse is equal to A into A inverse, and at the end we conclude that this product is again equal to identity. So it is the proof of second part. Similar calculation can also be obtained as B inverse A inverse and AB product is equal to identity, and say B is invertible because its product with some matrix results in identity and its inverse is B inverse A inverse. We can say that AB inverse is equal to B inverse A inverse, and it can be generalized as if we have n matrices and we want to find the inverse of their products, we can also obtain in reverse order the product of the inverses of each matrix as shown here. And at the end we conclude that the product of invertible matrices is invertible and the inverse is the product of their inverses in the reverse order. Next, our example is related to the inverse of a transpose. We consider matrix A, which has first row A, B, and second row contains the elements of C and D. We obtain the transpose of A, which is shown as the first row becomes the first column and second row becomes the second column. Since A is invertible, its determinant is non-zero, and we know that the determinant of A will be equal to AD minus BC. If we say that A is invertible, then its determinant is not zero. But let's check the determinant of the A transpose, and it's again AD minus BC, which we have already assumed that AD minus BC is not equal to 0. Therefore, A transpose is also invertible because the determinant of A transpose is not equal to 0. Let's see here. We want to find out the inverse of the A transpose. We have divided the adjoint of A transpose by its determinant, and we obtain 1. Now we know that A inverse can be calculated easily, and when we take its transpose, it's calculated as in equation 2, which is the same as equation 1, and therefore from 1 and 2 we conclude that the inverse of A transpose is equal to the transpose of A inverse. Now we see the inverse of a product. If we are given the two matrices A and B, we will calculate the product AB, and then we calculate its inverse. We know that the inverse of any matrix is equal to the adjoint of that matrix divided by the determinant of that matrix. And if we want to calculate the inverse of AB, we will take the adjoint of AB and then we will divide the adjoint by the determinant of AB, which is calculated here. Determinant is minus 2 and the adjoint is described in the given brackets in this matrix, and we obtain the inverse of AB as 4 minus 3 minus 9 by 2 and 7 by 2. This is the 2 cross 2 matrix. Similarly, we calculate A inverse. A matrix is given and we calculate its inverse, and on the same pattern we calculate B inverse, which is equal to adjoint of B divided by the determinant of B. Determinant of B is equal to 2 and the adjoint is 2 minus 2 and second row minus 2, 3. We obtain B inverse. Now we take the product of B inverse, A inverse. We observe that the product is the same which is obtained before the inverse of the product of AB. Hence, we can conclude here that the inverse of AB is equal to B inverse A inverse. This theorem states that if A is invertible and n is a non-negative integer, then An is invertible, and the inverse of An is equal to A raised to the power minus n, and which can be written as A inverse whole power n. And the second part says that any non-zero scalar k, if A is invertible, then k is also invertible, and k a whole inverse is equal to k power minus 1 A inverse. Related to the above theorem, there is an example. The matrix A is given. A is 2 cross 2 matrix with the entries 1, 2, 1, 3. We can easily calculate inverse of A. A inverse is calculated here. We will show that A power minus 3 is equal to the power 3 of A inverse. Let's take the product of this matrix 3 times, and we know that how we have to multiply these matrices. We conclude this product is converted into a single matrix which has the identity, which has the entries 41, minus 30, minus 15 and 11. Similarly, we take A cube, which is obtained in a matrix form, single matrix form, which has the elements of 11, 30, 15, 41. Now we take the inverse of A cube, which is adjoint of a matrix divided by its determinant. Its determinant is evaluated and multiplied by its adjoint, which is obtained by interchanging the place of 11 and 41 and changing the sign of 30 and 15. And we note that this result is the same as that of A inverse whole power 3, which is already calculated above. Now we want to discuss about elementary matrix. We know about the elementary row operations. that can be performed on a matrix. There are three types of such operations. Can interchange any two rows. We can multiply to a row by a non-zero constant and adding a multiple of one row to another. These are the three operations which we can apply on a matrix. These are the row operations. And an elementary matrix is a matrix that results from applying a single elementary row operation to an identity matrix. That if we have an identity matrix and we apply any one of the row operations, the new matrix will be called the elementary matrix. An n cross n matrix is invertible if and only if A is row equivalent to In, and in this case any sequence of elementary row operations that reduces A to In also transforms In into A inverse. This is an interesting theorem that if we apply row operations to transform any matrix A to identity matrix, the same operations which we apply on identity matrix transforms the identity matrix into another matrix which is called the inverse of A. How can we find the inverse of A? If we place A and I side by side to form an augmented matrix AI, then row operations on the matrix produce identical operations on A and I. Then either there are row operations that transform A to In and In to A inverse, or else A is not invertible because there is possibility for any matrix to be not invertible. Find the inverse of the matrix A if it exists. Let's see in the solution we obtain an augmented matrix where we have placed the identity matrix on the right hand side. Now we will apply the row operations to make our A matrix to transform a matrix into identity matrix. Definitely then the right side, the identity matrix will change its entries. First we want to bring 1 as its first entry of the first column and first row. We will interchange row 1 and 2. The second row is placed on the first row. Similarly, now we apply another operation and we add minus 4R1 in R3 to obtain 0 in as our first entry of the third row. Next we apply 3R2 plus R3 to obtain 0 in the last entry of the second column. Similarly, minus 2R3 plus R2 change the third column's last entry as 1. And at the end, minus 3R3 plus R1 change our A matrix into the identity matrix. Since A is converted in identity matrix, we conclude that A is invertible and its inverse is right side of the augmented matrix, which has the entries as shown as in A inverse. It is a good idea to check the final answer. We can check that the inverse we have calculated uh, gives the results as identity matrix when we obtain the product of A with A inverse or A inverse with A. Hence A is invertible. Thank you very much.